Developing and operating microservice-based applications on modern cloud platforms. My name is Michael O'Sullivan and I am a software engineer at IBM in Cork in Ireland, where I work as part of the IBM API Connect team. So this is the accompanying video for this lecture, which I delivered at University College Cork here in Cork City in Ireland back in November. And this video covers the demo portion that I delivered in the lecture. I didn't have a recording of that, so I'm now going to make a recording available that will accompany these slides when I upload them. So I'm not going to go through all of these slides again, because you'll be able to do that where I have put these slides online, and you can just watch this video to accompany what I've already covered on these slides. So what I'm going to do here today is essentially start by reiterating from these slides that the demo you're going to see takes place on Red Hat OpenShift, and I have a series of demo applications available to show you. And through this demo, we're going to be covering aspects of not only deploying and building, but operating software on a modern cloud platform such as Red Hat OpenShift. And you'll be able to see exactly what value and what advantages that there are to actually running an application on a cloud platform such as this. So this is the application, or rather the demo I'm going to show you. I have 3 applications, so this is just an overview of what those are. So as I've mentioned before, Red Hat OpenShift is essentially an enterprise release, or an enterprise edition of Kubernetes. It's powered by Kubernetes, and I do have a cluster running OpenShift, and on this cluster I have 3 sample applications. So I have a front-end application, which is our UI, our user interface, written using Next.js, which is a framework for developing web applications with React.js, that very famous Facebook JavaScript library. We have 2 back-end applications. One is called an employee service, which is written in Go, or Golang, which is the Google programming language. And then last but not least, I have the projects service, which is written in Node.js, using the Express.js library for implementing simple routing of endpoints. So these 3 all exist inside one Kubernetes cluster namespace. There's a Kubernetes deployment for each of them, and this is a microservice application. It's one application made up of 3 separate running services. I should point out that because this is OpenShift, we deal at the project level. So essentially a project in OpenShift will map to a namespace in Kubernetes. The way this project works is that from your laptop, or my laptop in this case, I will send a GET request to this front-end service, which will download the minified artifacts, client-side JavaScript artifacts for rendering the user interface in my web browser. The web browser will then, based on the JavaScript for my front-end application, is going to make a request to this back-end employee service running inside the cluster to download a list of the employees of the team that I work on. And in turn, that service, the employee service, is going to send another HTTP GET request to the project service to get a list of the projects that each employee on the team works on. So essentially, we're encapsulating different domains of responsibility for each of these microservices. The employees microservice just has information about the employees, whereas the project service contains the information about what projects we have in our team and what employees are working on them. And I should point out, of course, that this is entirely fictional. It doesn't correspond to the way we actually manage projects. This is just a demo application. I also additionally want to point out the organization of the net requests here. So the front-end application Next.js, I'm not a Next.js expert by any means, or by any stretch of the imagination. One of the differences between Next.js and raw React.js is that, unlike React.js, Next.js divides up essentially React components between components that are rendered server-side and components that are rendered client-side. Whereas in pure React.js, all components are rendered client-side. And therefore, for the purposes of this demo, even though I'm using Next.js, I actually don't have any server-side render components. So all the components of the UI front-end are rendered on the client side on the laptop, which means that when the application, the front end application, makes a request to get the list of employees, that request is originating from the JavaScript code running within my web browser for the front end UI application. That's why there's no arrow from this microservice, the front end, to the employees service. It's not the server-side front-end application making a HTTP request to the employee service to get the list of employees. It is the running client-side JavaScript on my web browser. So that is the setup of our demo that we're going to look at today. Here we are now on the demo Red Hat OpenShift cluster, and this is the user interface console for working on that cluster. So this is deployed on an internal server here within IBM. It's not publicly accessible. So what I'm going to do is I'm going to just have a quick run through this. So basically, this is the administrator view of the Red Hat OpenShift console, and I can get an overview of all the activity happening in my cluster. Now, like the lecture, this demo assumes that you know something about Kubernetes, Docker, containerization, etc. I'll elaborate very briefly where I can here. But this lecture was delivered to students on the UCC Computer Science Cloud Infrastructure and Services module, where I knew they had covered some containerization and clustering with Kubernetes already. So I'm not going to reiterate all aspects of that. I will where necessary and where it's straightforward enough to do so. So I'm not going to take you through an in-depth tour of the OpenShift administrator view, because that's not what the scope of this talk is all about. It's about the application view. So what I'm going to say here is that within the administrator section of the console here, I have created a UCC project within this cluster, right, which maps to an underlying Kubernetes namespace, also called UCC. And that's it. With that, I'm going to flip over to then the developer view, which is the view of the OpenShift cluster for an application developer, which is the approach we're taking today. So this, I'm more used to working in the administrator view in my day-to-day work. But this, and you can see this view has fewer options compared to the administrator view, but it's enough to get going with what we need to do in this demo today. So if I click on, before I even walk through this, if I click on topology here to look at what's in this UCC project already, I have already deployed two of the applications in the diagram I showed from the lecture slides. So I have the user service, which is the backend service, which lists all the employees of our team. And that was, as I said, that was written in Go. And I have this Carbon Next.js, which is that front-end user interface application, which is also running in this cluster as well. I would note that it says Node.js, so under the covers, it is a Node.js application that the Next.js application is utilizing. So that's why we see the Node.js icon. And these are both, from this gray box, part of one app, which is simply called User Service Go app. And I already deployed these before I started this lecture. So they're both healthy. You can see the little green tick, and they're both built and they're running within this cluster and available for use. So you can actually see here that both of these applications are available via a URL. So here's already straight away the application is, or rather the cloud platform is providing me with a route, a URL to be able to publicly access the application on the public internet. So if I click on, or rather, because this is an internal IBM application, you would need to be in IBM to access this, but in theory, the route can be totally public. So if I click, just to give you a quick rundown of the application for real, if I click on open URL for the UI application, which is here, I get a new tab in my web browser, and here we go. So this is my sample UCC Computer Science demo application for this lecture, built using Next.js. So all I have here is before I elaborate on what I have here, all the UI styling and CSS that you see here, it was built using the Carbon framework. And Carbon is IBM's kind of web component styling framework that we use consistently across all of our applications and services that we make available on the cloud to provide a consistent look and feel. So Carbon is the IBM kind of UI component framework or library for our web applications. So I decided to use it here for this one. So all I've got here is a bit of information about me. Who am I? Michael. I've already told you I work at IBM Cork as part of the API Connect team, and I have a little bit here about what API Connect actually is. It's part of the IBM automation portfolio, and it is a product that allows organizations to build, manage, enforce, socialize, and monetize their APIs, which all happen in the form of open API documents. A bit more about me, because why not? I am an employee of IBM since September 2015, where I started as part of the IBM Cloud dedicated and local team. The very first project I worked on was the logging and monitoring service for that product. I am a graduate of the CK401 Computer Science course at UCC in Ireland, for which I graduated in 2012, and then even before I graduated from that, I started a PhD in computer science, also in UCC, in 2012, and I was conferred with that in February of 2016, at which point I had actually already started working for IBM. Now, more so to the point of this demo, if I click, you can see up here I have a link that says employees. So if I click on this, I get a table with all of the employee information from that user's backend service, which is this one here. And in fact, if I click on the little link for this one, I'm taken to the user service. Now I get a 404 page not found, because actually this is not the whole URL of where we need to be. If I put in /employees, I get back a JSON object, or rather, yeah, JSON object with a list of employees. So we have, there's me, ID number 1, Mike with role engineer, and then an entry for all the other employees on this team as well. We'll look at that in a bit more information, more depth shortly. So so basically this all looks pretty good. So I've kind of shortened the names of some of my colleagues here and given our roles. So this corresponds to the team I do work in as part of API Connect, and we can see these are fictional IDs, but these are shortened names of who the real people are. Each person has a role. And then over here it looks as if there's something wrong. We have a list of projects, but it says projects are currently unavailable. So why is that? Why are the projects currently unavailable? So I'll share something with you. I didn't get time today to deploy the project service, so that's why it's not available. So right now, the third microservice in the diagram I showed you is not running in the topology of this cluster. So it needs to be deployed, and that's what we're going to do here as part of demoing the features of the cloud platform and what it can do for you. I would also, before moving on, I would also like to make the distinction that just because the project's microservice is not available, it doesn't mean that the whole application suddenly doesn't work. I'm not getting any errors here. The employee's application is still up and running. It's still providing information to my front-end UI, and it hasn't crashed ungracefully. So this is part of what we would call cloud native design. Our application, which is composed of a series of microservices, can gracefully handle failures of individual microservices in the application, even if it's just as simple as showing a message letting you know that that particular part of the data is currently unavailable. So that's something to bear in mind when you're developing applications and microservices for the cloud. Just because one part of it's not available or not deployed right now, it doesn't mean that the whole application should stop working. The last thing I want to emphasize before we move on is I just want to open my network tab, and I want to just show you again, if I refresh this page, we can see, just to allude to what I said in the introduction about the sequence of network requests, that we can see here that my web browser has made the call to the employee's service on my cluster, on my OpenShift cluster. So that wasn't initiated by the backend, that was initiated by the JavaScript code of the Next.js application, in particular for this particular React component running in my web browser, and then making the call to the server to get the list of employees. And then we can see the response is provided here. Now, what I want to do next is, in fact, I'm showing you the wrong thing altogether. It's this one. It's this one. This is the request to get the employees. So you can see here, if I look at the response here, there we go. There is the response data that we get from the employee service in JSON format. sorry, that first link there is actually for downloading the HTML of this web page. So that's the JSON response that has been received from the employee service on the back end. Okay, I will close that, and what we'll do now is we'll deploy the project's application. So to do that, I'm going to go to the Add option here, which is the home page of the developer view, and you can see that the platform here, the OpenShift platform, provides me various different ways of deploying applications onto the cluster. One of which, what I really like, is to import from Git. So by simply checking the source code into Git, OpenShift is capable of finding the project in GitHub and actually building it and deploying it onto the cluster for me. So again, more value from the cloud platform. So if I come over to my own personal GitHub here and click on repositories, I have the 3 microservices actually deployed here. So there's the user service, there's the Carbon service, and then here's the project service that we're going to deploy next. So like I said in the introduction, this is a simple Node.js application with the Express framework. You can easily tell by means of package.json that it's a Node.js project. And if I look at app.js here, we can see I actually do have an identifier of projects. What are all the projects, which are fictional by the way, that are available on our project server. So what I'm going to do is I'm going to come over to here and I'm going to enter the URL of the project service in GitHub, which is this one here. And those repos, by the way, are public for the purposes of this demonstration. And we can see here by entering the URL to that project service in GitHub, the platform has looked at the files in that repository and it has correctly detected that it's a Node.js project. How does it know that? Well, it can tell by means of the package.json file. If I were to, for example, show you the users project, which is written in Go. If I put the URL in for that in instead, now bear in mind I've already got this deployed, so I won't deploy it again. You can see that by looking at this project, the platform can see that it's a Go project and that it needs to use a Go builder to build the project, a Go builder image. And how does it know that? If we go back here and we look at the users project, which is here, again, we can see that this is a Go project, of course, because we have files with the .go extension for Golang, which is here. So microservices, of course, can be built in different languages of your choice. You don't need to keep them all consistent. And of course, we have the typical go.mod and go.sum files that you would expect to find for any Go application. So the platform has intelligence enough to look at the files in the repository and figure out what kind of application it is, and therefore what builder image is needed to build it. So let me put this back to the project service. Now let's elaborate there for a second. What do we mean by builder and builder image and building the project? So if we go back to the project service here, these are not compiled artifacts. We have got an app.js, these are source files. We don't have a Docker image here or reference to a Docker container. We don't have a single binary executable. We just have source code like this one, right? So we need to build, so this project needs to be built into something that's actually runnable, for example, as a container in a pod on our Kubernetes cluster, which in this case is Red Hat OpenShift. So these source code files need to be built into something that can run as a container on the platform. And that's again what the platform, the Red Hat OpenShift platform, is doing for us. It's detected that it's a Node.js project and it's going to build it using Docker, a Docker image, a Node 16 Docker image, and build it into a runnable Node.js container application. So again, it's detected that it's Node.js 6. I could tell it to use something else. So it can detect Perl, PHP, Nginx, HTTP, .NET, Go, Ruby, Python, Java, JBoss again, and Node.js. Or that's if you want to use a builder image. Or you could even provide us a raw Docker file. If you had a Docker file where you've defined yourself as to how the container for the application should be built, you could just simply put in the path of the Docker file. And then it's got dev file, and in fact, I don't even know what dev file is. So, but for the meantime, I don't have a Docker file for this application. We're going to revert to the builder method. So I'm going to change the resource type to deployment config, which is a type of resource that Red Hat OpenShift can use to determine and help us build new changes to the project rather than a pure Kubernetes deployment. and the target port. What is the port that this server is listing on? And if I recall, if we go back to my Git repo in here, in app.js, I think this is listing, yeah, it's listing on port 4000. So 4000 is the port that we need to tell OpenShift to send traffic into. So in other words, you can see here, it's asking for the target port. And we've got a box here that says create a route, which means expose your component at a public URL. So by checking this box, it'll create a public URL for users to access this application on the cluster. And by configuring the port, it means that whenever traffic comes into the cluster on this route, it will send the traffic to port 4000 for this application. And with that, I think we're ready to go. So we'll press create. And we'll wait, and there we go. So it says resource added, deployment config created successfully, and it's also created the route project service node.js ecc.apps. etc 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 .fire.ibm.com. So that's the publicly accessible URL for this application. Now it's not built yet. It's now been added into the application view here. So project service node.js. There's no running pods, Kubernetes pods for this application yet. But what we see here is, well, there is now, it's coming, but I wasn't quick enough. But it built the project. So you can see here, build number 1 was complete just now. And when it finished, it kicked off the running pod for that application. So if I click on view logs, just out of interest, these are the logs for the build. So what we can see here that Red Hat OpenShift has done for us is it's checked out the code from Git, and it's using a Docker file, a Node.js Docker file. You can see here an OpenShift Node.js Docker file to build a Docker container with the contents of the application that it checked out from GitHub. So you can see there, it copied the source from GitHub into the container and built it and assembled it. Installed all the dependencies, which means for a Node.js application, it would have run an npm i to install all the packages for that application, and then push the image for that built application to an internal service registry, an image registry. Here, successfully pushed this image to the registry, push successful. So with the built image for the application pushed up, it means that the application can actually run as a pod in the cluster, which is what we just saw over here. So the pod is now running with that image. So you see project service is now running, and we could look at the logs for that running pod as well. And it says here that the project is now up and running and listing on port 4000. Great. It looks like we're almost done. So we'll go back here again. Just to emphasize as well, here is the route that was created with the public URL to access our application. And if you know something about a bit about how Kubernetes works, this route actually, which is public facing, when traffic arrives on this route into the cluster, it's actually sent to the service, which is this guy here. So it also created this service for us, which sends traffic, which maps incoming traffic from the route to the right running pod. So if we have a look at, if we were to look at this route, for example, at this public URL, we can see that it's configured to point to the project.js service. We can look at the YAML specification of that just to see what that looks like. There's our public facing URL, also configured up here, and it says when any request arrives to this host, send the traffic to the project service node.js on port 4000. Just to re-emphasize that, then if we look at the service, which is here, so the ingress or the route is going to send the traffic to the service. And if we look at the services in Kubernetes have what's called a pod selector, which is based on labels. So it says when traffic arrives into this service, send it to the pod with the label, with an app label of project service node.js and a deployment config label of project service node.js. And if I click on this, it'll show me all the pods in my cluster that match that label. And you can see here it's listed the project service pod that we just saw and looked at the logs for. It's ready one of one. So just to emphasize now, if I go back to topology and I click on the route here and open it, I'm prompted. This is because it's an internal cluster. It doesn't have a signed SSL or TLS certificate. I need to say I want to accept the unsigned certificate and proceed. And this is now taking me to the application. which just says cannot get /. So if I look at the source code of this application, it tells me I need to send a request to /projects, which will send back in JSON format the list of all the projects that we have on the team. So if I change this to say /projects, we now get back a list in JSON format of those projects with project IDs, project names, and descriptions. Great, it looks like we're all settled. It looks like we're ready to go. So if I now open my front-end user interface again, which is on the Carbon service, and go here, and this time I click on the employee service, I would hope that I'm going to see for every employee all the projects that they work on. Oh, I don't. It says currently unavailable. So something else is not right here. It's not working. We should see the names of the projects that the employees are working on here. But it still says currently unavailable. So something has gone wrong. So let's have a brief recap before we continue any further. We've seen already some of the advantages of operating and deploying applications on a modern cloud platform. It manages the applications for us. It manages the routing for us of those applications by means of the URLs that route traffic into our application. It's even able to build the applications for us from source code. And once it's done that, it's then able to put them as running on the cluster in a Kubernetes pod using the container that has been built from the source code. We've also seen that the platform can even show us logs for the applications that we're running. And in fact, well, I'll say no more. We'll come back to this shortly. Okay, so we can see here that we're able to see logs for our running application to tell us a bit about what's going on. So we'll take a brief pause here, and when we come back in the minutes, we'll try and then see another part of running an application on a modern cloud platform is how can the modern cloud platform be used to help us monitor and observe and debug problems that are happening with our running applications. Okay, so now we're going to explore, as I mentioned, how we can use the capabilities and features of the Red Hat OpenShift Cloud Platform to help us diagnose and troubleshoot exactly what's not working here or what's gone wrong. So we know now, even though we've now deployed the project service, we still can't see the projects listed here. So if we go back to the topology, you might recall that from this, for each of these applications, a route was created, and we actually saw this earlier. So if I click on the icon here to open the public route of the project service, and I navigate, as we saw in the code, to /projects, like so, we do get the list of projects back. So it's not as if the project service isn't up and running properly. It is, and in fact, we can reach it. So it must mean that the issue has to lie somehow as to why the user service cannot actually get the information from the project service. If we refer back to the slides for a moment, we can see that it's not the web browser or the front-end JavaScript code running in the web browser, to be more precise, that calls the project service. The employee's microservice that we're talking to is what in turn calls the project service to get the list of projects. So something is not working between the employee service and the project service. So the question is, the challenge for us is how we can use the cloud platform to help diagnose and troubleshoot this problem and ultimately fix it. So the first thing to have a look at is let's have a look at the logs. So I showed you earlier that one of the features of the cloud platform is we can look at the logs of our running application. And this idea of looking at logs or metrics for applications is under the umbrella of what we call observability of an application running on a system. And we can see here that there is an observe option in the Red Hat OpenShift UI, but logs actually appear slightly differently. So I'm going to now show you a different view just to kind of show you the full features of the platform. So what I'm going to do is I'm going to click on project, and in here what I'm going to do is it shows me an inventory of all of the different objects or resources that I have deployed in the UCC project on this cluster. And I can see here it says 9 pods, and remember, a Kubernetes pod is what is running all the containers that we built for each of these applications. If we were to take the Next.js application, which is the front end, we can see there's a deployment pod which is marked as completed. That's because it was a job. We have long running pods and then pods that run as jobs, meaning they complete a particular piece of work and then stop in a completed state. So there was a job for the deployment. There was a job for building the application from the source that we imported from GitHub, but then we have the actual running deployment up here, ready one of one. So we see those three types of pods for each of our three different microservices. So what I'm going to do is I'm going to order them by most recently created, which is this one. And what I'm going to do is I'm going to look at the logs of the project service, which is this one here. So this is the pod for the running project service. And if I have a look at the logs of this one, this is interesting. So we can see here that this is running on port 4000, as we saw earlier, but there's no errors in this log. There's nothing in here to indicate that something has gone wrong. So this would lead me to believe that the issue perhaps is not with the project service. So if we go back, that means the next port of call to investigate would be the user service, which is what's supposed to query the projects. So we can see the running user service pod here. So I'll open that. I'm going to have a look at the logs of this one. And oh, very obviously, the log is actually full of errors. So let's look at the last one. It's the same one over and over again. So let's have a look at the last one. Calling localhost. Oh, well, there's the problem. It's calling localhost like it would when I was developing the application on my laptop. So this clearly isn't right. We know that the URL of the project service is, of course, the host name of this particular cluster, which is this entire address here. So it certainly shouldn't be querying localhost. So it's trying to query localhost 4000 to fetch project with ID number 2. And as one would expect, it gets a connection refuse error. It cannot talk to localhost on port 4000. So localhost would refer to the machine that the pod is running on in the cluster. So this isn't going to work. And this, of course, reminds me of exactly why this isn't working. So let's go look at the project code itself. So if we flip over back to the source code, and I can show you exactly what the issue is here. If we look at the user service, which is here, and we'll look at the source code in main.go, and I scroll down. So we need to find out, if you're debugging, you might say, well, it's trying to talk to localhost. So do I have any references to localhost in my code? And it says I do. So we have a function here, get employee projects, which is supposed to get the list of projects that a particular employee works on. And it says if project service URL is equal to empty, then set the project service URL to be localhost 4000. So we are obviously dropping into this loop here, which means that project service URL must indeed be empty. And of course, if I look for project service URL in my code, I can scroll back up here. And what I expect to find, yes, I'll just get this out of the way, is that project service URL, get rid of the yellow here, is being read from an environment variable called project service URL. Now, let's see, have I got that variable set on my deployment on Kubernetes for this particular application? Although you might guess the answer is obviously no, because we're falling into that localhost block of code. So let's have a look. I can see this on the OpenShift platform as well. So not only does the OpenShift platform provide facilities, as we've seen, for building, deploying, running, and observing our applications, it provides capabilities to let us configure our applications. Now, again, if you know anything about, well, let me step back a bit. When we deployed the project service, we created it as a deployment config, and the deployment config actually defines the running pod. So let's have a look at the pod itself. If we go back to details of the pod, we can see here that there's an environment tab. So if we click in here, and we can see all the environment variables that are set in this container by the deployment config. And as we can see, actually, there's none. That's obviously the problem. So if I click on YAML, because of course the OpenShift console is just reading this information from the actual YAML definition. YAML means yet another markup language. It's a very popular syntax for defining and configuring different types of resources in software development. So this is the definition of the pod in Kubernetes. So if I scroll down into the actual definition of the running container within the pod, there's the image that was built for me, and we can see here there is no env section, env. So you would expect to see an env section defining any environment variables for this pod, and there isn't any. So let's create one. Okay, so we'll go back to topology, and we'll open the deployment config of the user service. So we'll say edit deployment config, and down here you put in the value of the environment variable without the slash, and save. So we're now going to get a new users pod. Okay, which is container creating. So you can see rolling out the updated pod number 2. And we wait for that to deploy. And what we can do, oh, there it is. Now it says it's running. So now let's try it one more time, and hopefully we'll have success. Yay, we are now up and running. So now the user service is able to talk to the project service, and it gives us the names, which are fictional of course, of the names of the projects that each team member, each of these employees is actually assigned to. So that was an interesting illustration of actually two things. Number one, how we can use the platform to debug issues and troubleshoot problems, and two, how the platform allows us to configure the behavior of our running applications. Just to reinforce that, if I now look at the logs of the user service, we would hope not to see that error anymore. And we don't. We can now see calling the project service to fetch the projects, and we don't see any errors. And we also see the log for me actually accessing the employee's endpoint on the UI as well. So great, our application is now up, running, and healthy and functioning as we would expect it to do so. There's one other thing you might ask of me. You might ask, why is it that I don't put the URL into the source code? Why am I reading it? Why am I reading it as an environment variable? And of course, that wouldn't be cloud native design. This is one of the reasons we use cloud platforms, is that the configuration for the runtime of the application is injected by the platform at runtime. Because if we were to put the actual URL in here, it would mean we'd need to compile a separate version of the code for every location where we run our user service, which is not cloud native, it's not scalable, and it's a maintenance nightmare. It is worth noting, for example, if I did want to make a change to the code of the application, one of the nice things about running on the Red Hat OpenShift platform is that we've already seen it deploy for me. But it also means that if I do push an update to the code into GitHub, that I can actually consume that update in here by having it rebuild. So for example, let's say I pushed a change to the user service. So I click on that. If I press start build here, what that's going to do, and I have pressed it, there we go. So now it says build number 2 running, which means that it will now go to GitHub, fetch all the source code again, and rebuild a new image with all of the updates to the source code that have gone into GitHub since I last built it. And once it is finished building, it will deploy that updated pod with the updated code right onto my platform for me. So yes, another example of the cloud platform actually doing work for me that would be a very manual process to do otherwise. Oh, there we go. So that build is now completed, and it's now running out pod number 3. Now, of course, in this example, I didn't check in any changes into the code into GitHub, but you can now see that not only has it built based on the updates from GitHub, if there were any, it has actually rolled them out to the platform as well. So the platform here has proven very beneficial so far for observing what is going on the cluster, getting my applications deployed, and helping me debug issues. In the next section now, I'm going to talk a bit more about observability and scalability on the cloud application platform. Okay, so the last item I'm going to show in this demonstration covers observability and scalability of the cluster that can be provided by the cloud platform, and these go somewhat hand in hand. So as I alluded to earlier, there is an observe tab or page over on this on the side of the console, and what this does is it will give me a dashboard of the usage of CPU and memory across all of the workloads, i.e. the pods on the cluster. such as CPU, memory, network usage, storage usage, etc. Now, so for example, I can see here I was experimenting with this a little while earlier to find the most effective values for a demonstration. So we have graphs and tabular views of things like how much CPU and memory all of the pods have used on the cluster. So what I'm going to do is I'm going to use this as a demonstration of how the cloud platform can be used to horizontally scale the number of pods on the cluster to deal with additional workload under stress. So what I'm going to do is I'm going to come back to topology here, and I'm going to use the user service as a demonstration of this. So I'll click into the user service, and what I'm going to do, I'm going to show you what's called the resource limits. So on a Kubernetes cluster, this isn't specifically Red Hat OpenShift, you can define what's called the request and the limits for CPU and memory allocations for a pod. The request values indicate how much CPU and memory must be available on the underlying worker node in the cluster in order for Kubernetes to run a particular pod on that worker node. Limit then is the maximum number of CPU and memory resources that a pod is allowed to use on the worker node. Now in Kubernetes, the memory one, for example, the memory limit is a hard limit. If a pod tries to use more memory than the limit actually defined for that pod, Kubernetes will actually terminate the pod, or to be more precise, it'll kill it with an out of memory error. Whereas the behavior for exceeding CPU usage is actually undefined. If it can, the CPU usage can actually break through the limit, but it is subject to termination and or unpredictable behavior if that amount of CPU limit is not actually available. In some circumstances, Kubernetes will actually throttle the CPU allocation to the pod as a penalty for exceeding the limit. But in general, the behavior is undefined compared to the memory limit, which is a hard kill scenario. So what I was playing around with this earlier to find some effective values for the demonstration, as I said, and what I've done is for the user service, I've defined a CPU request of 5 millicores and a memory request of 10 megabytes. For the limit of the CPU, I've set 15 millicores, while the limit of the memory I've set to 100 megabytes. So those are the resource requests and limits defined on the user service. And with those defined, what the cloud platform, or even Kubernetes to be more precise, allows me to do is define a resource called a horizontal pod autoscaler. And I created one earlier. And what this does is it allows Kubernetes to, under your control, determine how the user service in this example will actually scale. So this horizontal pod autoscaler, that we often abbreviate to HPA for short, has a name of example. And it said that for the user service, I must have a minimum number of 1 pod running at all times. But I will allow it to scale to a maximum of 5 pods. So then how does it determine under which criteria it should scale the user service to 5 running pods? And for this demonstration, I'm going to use one metric, which is CPU utilization. So I've set it to 10. And what that means is if the average of the CPU utilization for the user service exceeds 10 millicores, then what it will do is it will then scale up to a maximum of 5 concurrent pods for the user service. So I've created that. So I don't need to press save there. So what I'm going to do is if I go back to project and we look at the pods at the moment. So I have 16 pods in total right now. At the moment, I'm on version number 7 of the user service, but there's only 1 pod running. So again, we have the deployment pod, but we don't have any other running pods aside from this one. So what I'm going to do now is I'm going to click into I'm going to click into observe and set ourselves up here. So I'm going to switch to a different dashboard that's a bit more concrete to the workload for the user service. So I want to look at the workload metrics for the deployment config for the user's service. And this was me playing around with it a bit earlier. So what I'm going to do is I'm going to adjust the time range to the last 5 minutes, and this is going to refresh these graphs every 15 seconds. And this is where we're standing at the moment. So like I said, we have our CPU limit set for the user service to 15 millicores as the limit, and I made a request of 5. So our current request percentage is sitting at 5.71%. Now, what I'm going to do is I have a tool over here called Vegeta, which is named after a Dragon Ball character, and I haven't seen a lot of Dragon Ball, so I don't know which one, which character it is. So what this is going to do is I'm going to send a GET request to the employee's endpoint of the user service, a HTTP GET request. So then I'm going to pipe that into this Vegeta attack command. Attack is obviously what Vegeta does in Dragon Ball. And for 60 seconds, for a duration of 60 seconds, Vegeta is going to spawn 1,000 worker threads. And each of those 1,000 threads over 60 seconds is going to send a request to the employee service, get a response, and then it will do it again, and it will do it again and again and again for all of the 1,000 threads over the 60-second period. And what we're going to do is we're going to watch the metrics and see how the scaling behavior runs based on what we've defined in the horizontal pod autoscaler. So I'm going to run that now. So that's running. I'll switch back to the console. And what we're just going to do now is I'm going to come back to project very quickly and open the pods view and order by created time. And we're just going to watch now for a moment. So we're still only on one pod for the user service, ready 1 of 1. And assuming that the 1,000 threads hammering the user service will exceed the average of 15 millicores that I've requested as the limit for the user service, we're going to see some new pods crop up on this list. There we go. Oh, right on time. So we can see there now the horizontal pod autoscaler has just provisioned 3 new pods to run alongside the original one. So we've now got 4 running instances of the user service that the root will distribute the traffic to evenly. And actually, look, a 5th one has just come up now as well, which was the maximum. We declared a maximum of 5. And sorry, we said for the horizontal pod autoscaler, we said if it exceeds an average of 10 millicores that it would trigger the scaling behavior. So now let's have a look at the observability again. And we'll switch into the workload view for the user service for the last 5, and you can even see here for the last 5 minutes we've now just seen the graph actually of the CPU usage actually scaling up. So we can see there that for all of the user service, we've actually now reached 15 millicores, which exceeds the 10 that we defined as the threshold for scaling in the horizontal pod autoscaler. So if I come back to that's why the horizontal pod autoscaler kicked in. So if we now come back to the project view and look at our pods, and again I'm going to order them by when it was last created. You can actually see one of the pods is actually restarted. So with the initial configuration of resources and resource requests and limits I've defined on the pod, this actually wasn't even enough to handle that 1,000 worker load for 60 seconds. So this pod here was presumably killed. So if we come in here, or restarted rather, and we can see that if I look at the logs, there's a previous log from the previous execution of the pod, and we can see some errors here. So there are some timeout errors here talking to the project service. So even the project service couldn't handle that amount of requests over the 60 seconds. But this means that this pod actually was killed and restarted, presumably because it exceeded the memory allocation. So I could have also configured the horizontal pod autoscaler to scale on a memory threshold as well. So let's go back to the pods, and if we look at the output of the actual Vegeta tool, we can actually see here that it wasn't 100% successful, and you can see some of the requests actually timed out. So this level of resource specification and the horizontal pod autoscaling I actually defined actually wasn't enough to deal with that level of load. So this is the kind of behavior and simulations you can do from a performance perspective and use the observability tools of the platform to get an insight into how your application is behaving so that you can define appropriate scaling policies for the type of workload. Now, if we now the test is now finished, but if we waited more than 5 minutes, which is the default value, the horizontal pod autoscaler would actually delete 4 of these pods and bring it back down to 1 pod. So that horizontal scaling, it's scaling in and out based on demand. Okay, so that's a demonstration of the scaling and observability features of the platform. Okay, so I just waited a couple of minutes, and I can see now at this point we're back down to 16 pods. So the horizontal pod autoscaler has now scaled us back down to the minimum of 1. And I can actually see it over here on the right hand side in the activity view of the cluster. Just 1 minute ago, the current time on my laptop is 21:57. So we can see here at 21:56, the HPA emitted an event of new size 1 and deleted some of the pods, or the excess pods, and brought us back down to 1. So if I look at the 16 pods, we're now just back down to the 1 user's pod. I can also see those events in the horizontal pod autoscaler itself, because it is a kube resource, just like a pod is a kube resource. So if I go search, and I filter the resources by horizontal pod autoscaler, there it is, there's the example one. And if I come in here and I look at the events, I can see a kind of there we go. I can see a visual timeline of when we undertook this work. So we can see here, for example, where did we start? We started up around here. We can see, no, not that one. Beg your pardon. What is this one up here? Sorry. Generated from horizontal pod autoscaler. New size 4, reason CPU resource utilization above the target that we had said of 10 millicores. So then it went up to new size 5. So we saw it create that last one. And then you could just see 2 minutes ago from now, it said new size 1. Reason all metrics are below target. So that's a visual view of the horizontal pod autoscaler in action. So last but not least, I forgot there was one thing I meant to show you earlier, which is another feature of the cloud platform. We talked about the configuration, and we fixed the user service by injecting an environment variable with the URL of the project service. So we can see that in action by using another feature of the platform. So if I go to project, back into pods, and again, if I look at the user's pod, the user service pod, it can provide an interactive terminal into the running container, which I think in this example, I think I have it based on, it's based on, I think it's either based on an Ubuntu container or a Debian container. Could be Alpine, I don't think it's Alpine. Anyway, I now have an interactive shell into the container. I can actually see some of the contents of the container. So if it says is that a directory, cd go? Yes, so we can navigate around the pod like this. So what I wanted to show you is if I run env, which is the shell command for listing the values of set environment variables, and I pipe that through grep -i on project, we can see here, aside from some of the Kubernetes default injected variables, which are these ones and these ones, right in the middle, we have project service URL equal to the URL of the route that OpenShift created for me for the project service. So that shows you that we can see the actual environment variable injected into the container as a configuration value by the platform. And we can see that by actually accessing the running container within the pod using this shell interaction that's available on the UI. And that, well, it truly is it. So just to summarize, I think what we've seen here today is we have covered in this demo a lot of the features that can be provided for you by developing on a modern cloud platform such as Red Hat OpenShift. So we've seen, for example, how it can be used to build and deploy applications from their source and run them on the cluster. We've seen how it can provide routing so that there is external ingress access to the cluster, and then routing of traffic between the different pods of the cluster. We looked at, for example, how we can configure settings and properties of our applications, such as when we inject to the environment variable to tell the user service where to find the project service. In fact, if I open this so that we can get a better sense of this, we've seen For example, how we can use the observability features of the platform to not only look at the logs of a running pod, but how we can get a real-time insight visually and into the utilization of the applications on our cluster in terms of CPU and memory and network resource allocation. And we've also seen then how those work hand in hand with the horizontal pod autoscaler and the resource limit set on our applications to dynamically scale on demand the number of replicas of our application to deal with an increased amount of workload. So these are the inherent kind of advantages you can have from running an application on a modern cloud platform like this one. Not just running it, but as we saw, building it and deploying it, using features like the logs and the observability to troubleshoot issues on the applications, and using the features to debug and then be able to rectify issues as they arise. So I think it's been a pretty fully featured demo, and I hope that you got some value from it and just got a bit of insight into how we can use the tools of a modern cloud platform to benefit our application development and deployment and life cycle by running applications on a platform such as this. So I'll share the links to these things in the original slide deck that accompanies this video, and I'd like to thank you very much for watching. And because it's almost Christmas time, I wish you a very happy Christmas or a nice winter break. Take care and goodbye for now.